4.9 Heat exchangers. Heat exchanger is a heat transfer device. It transports thermal energy from one fluid to another fluid. It is used to either remove or add heat from a system. Heat exchanger is widely used in food processing, power plants, automobile, refrigeration, and air conditioning. You may be familiar with boilers, radiators, condensers, evaporators, and regenerators. And these are examples of heat exchangers. Heat exchangers can be classified as direct contact heat exchangers and indirect contact heat exchangers. A mixing chamber is a direct contact heat exchanger. A common example of a mixing chamber is the mixing of hot and cold waters in a shower. We mix hot and cold water to get warm water. Typical designs of heat exchangers do not allow mixing. So hot fluid is separated from the cold fluid. Heat is transferred through the wall. In concentric counterflow heat exchangers, the fluids flow in the opposite directions. In concentric parallel flow heat exchangers, the fluids flow in the same directions. Fluids flow in perpendicular directions in cross-flow heat exchangers. We can simplify the general form of energy balance equation with appropriate assumptions. Heat exchangers do not involve any kind of work other than flow work of the flowing streams. So the change in the kinetic energy is small, it drops out. The difference in elevation between the inlets and outlets is small, so potential energy drops out. If we take the entire heat exchanger as the control volume, Q dot is 0, as long as there is no heat transfer between the heat exchanger and the surroundings. If one of the fluids is selected as the control volume, heat is transferred across the system boundary. So in this case, Q dot is not 0. So note that the basic energy conservation principle is valid no matter how we select the system boundaries. We'll need to determine the system boundary based on the required information we want to determine. Example 4.7. Steam enters the condenser of a vapor power plant at 0.1 bar with a quality of 0.95. So we know pressure and quality, so we can fix the states of the steam that entered the condenser. And condensate exits at 0.1 bar and 45 degrees Celsius. Also, we have pressure and temperature, so we can fix the state. Cooling water enters the condenser in a separate stream as a liquid at 20 degrees Celsius and exit as a liquid at 35 degrees Celsius with no change in pressure. Cooling water enter the condenser in liquid phase and leave the condenser in liquid phase. Heat transfer from the outside of the condenser and changes in the kinetic and potential energies of the flowing stream can be ignored. So there is no heat transfer between the heat exchanger and the surrounding, so Q dot drops out, and kinetic energy change, potential energy change are negligible, so the kinetic and potential energy drop out. For steady state operation, determine the ratio of the mass flow rate of the cooling water to the mass flow rate of the condensing steam. Also determine the energy transfer from the condensing steam to the cooling water in kilojoule per kilogram of the steam passing through the condenser. So first we need to determine the ratio of the mass flow rate of cooling water to the mass flow rate of the condensing steam. So here is a diagram showing the condenser. So steam entered the condenser at 0.1 bar and quality 0.95. Location here is 1. And leave the condenser at 0.1 bar and 45 degrees Celsius. Location here is 2. And cooling water enter the condenser at 20 degrees Celsius, location 3. And cooling water leave the condenser at 35 degrees Celsius. This is 4. So mass flow rate at location 1 is M1 dot. This is M2 dot, M3 dot, M4 dot. According to the mass conservations, M1 dot equals M2 dot, M3 dot equals M4 dot. And we are going to apply the energy balance on the condenser. There is no heat transfer between the condenser and the surrounding. Q dot drops out. There is no work involved in the condenser. W dot drops out. The kinetic energy change, potential energy change are negligible. And M1 dot equals M2 dot. M3 dot equals M4 dot. So we just need to determine the enthalpy at each location. At location 1, the pressure is 0.1 bar and quality is 0.95. 0.1 bar for saturated liquid vapor mixture and quality is 0.95. So what we need is the enthalpy for saturated liquid and saturated vapor. At location 2, the pressure is 0.1 bar, temperature 45 degrees Celsius. At 0.1 bar, saturation temperature is 45.81. And at location 2, the temperature is 45 degrees Celsius. So we know that is compressed liquid. So we can approximate it as a saturated liquid. Since the property is a strong function of temperature, not the pressure, and so we are going to use table 8.2. So at temperature 45 degrees Celsius, the enthalpy for the saturated liquid is 188.45. So H2. And we also need to determine the enthalpies at location 3 and 4. And we know that they are in liquid phase, 20 degrees Celsius and 35 degrees Celsius. And we are going to approximate them as saturated liquid, 20 degrees Celsius. This is H3, 35 degrees Celsius, H4. The ratio of the mass flow rate of the cooling water to the condensing steam is 36.3. The second question, we also need to determine the energy transfer from the condensing steam to the cooling water in kilojoule per kilogram of steam passing through the condenser. So if the system contains both the steam and cooling water, Q dot is 0. In this question, we want to determine the heat transfer from the condensing steam to the cooling water. So we select the system boundary for the steam. So this is our system boundaries. And we want to determine how much heat is removed from the steam. So we apply the energy balance on the steam. So note that Q dot is not zero. There's no work involved in the process. Kinetic energy change, potential energy change are negligible. So Q dot. And we already calculated the enthalpy at location 1 and 2. The negative sign indicates the heat is removed from the steam. On the other hand, the heat transfer rate from the cooling water to the steam is equal in magnitude but opposite in sign. So the cooling water received the thermal energy at 2276.7 kJ per kilogram, assuming there is no heat loss to the surrounding.